The expression for Newton's second law of motions is, sigma F is ma. The acceleration of an object depends on the mass of the object and the resultant of all forces applied on the object. The resultant and the acceleration have the same direction, and the resultant is the product of mass and acceleration. When an object is in equilibrium, its acceleration is 0. So the resultant, sigma F, is 0. Therefore, Newton's first law is a special case of Newton's second law. Let's look at an example. A force of 16 Newton is applied on an object of 2 kilograms on a surface with mu equals 0.5. Find the object's acceleration. As always, sketch the force diagram first. Vertically, there's weight and normal reaction. The object is moving to the right, so the friction points to the left. Let's look at both directions. The object is moving on the horizontal direction only. Therefore, on the vertical direction, there's no acceleration, and the resultant is 0. So R is equal to W, which is 20 Newton. This is Newton's first law. Horizontally, using Newton's second law, we have F minus friction equals ma. F is 16. Friction is mu r, mass is 2. So A is 3 meters per second square. It points to the right, in the same direction as the resultant on the horizontal direction. An object of 2 kilograms slides down on a slope with mu equals 0.3 at 30 degrees to the horizontal. Find its acceleration. First, sketch the force diagram. There's weight, normal reaction, and friction. Resolve weight on both directions. Vertically, the object's acceleration is 0. So R equals W cosine 30 degrees, which is 17.3 Newton. Horizontally, using Newton's second law of motion, we have W cosine 30 degrees minus friction is ma. Friction is mu r. Mass is 2. Therefore, A is 2.41 meter per second square. It points down the slope, in the same direction as the resultant. Object A of 2 kilograms is on a smooth surface. It is connected by a string to object B of 3 kilograms through a pulley. The string is taut. Find the acceleration of the system, and the string's tension. Object A is on a smooth surface, and B is heavier than A. So B falls down and drags A to move to the right. Since the string is taut, the value of the acceleration is the same. For object A, it points right. For object B, it points down. Now, let's sketch the force diagram for the two objects. For A, there's weight, WA. There's normal reaction. And tension T. For B, there's weight, WB. And tension T. Since it's the same string segment, the two T's are equal. For object A, on the horizontal direction, using Newton's second law of motion, T is ma times A. ma is 2. So T is 2a. For object B, WB minus T is 3a. So 30 minus T is 3a. Add these two equations, we get 30 equals 5a. So A is 5 meters per second square. And T is 12 Newton. What if the surface is rough and mu is 0.5? Then, there's friction acting on A. For A, vertically, there's no acceleration. So R is equal to W, which is 20 Newton. Horizontally, T minus friction is 2A. Friction is mu R, which is 10. So T minus 10 is 2A. For B, it's still 30 minus T is 3A. Add these two equations, we get 20 equals 5a. So a is 4 meters per second square. And t is 18 Newton. A car of 1,000 kilograms is towing a trailer of 500 kilograms with a connecting rod. The driver starts to brake and there's a constant resistance of 4,500 Newton. Find the deceleration and thrust in the rod. First, let's set the positive direction of acceleration. And then, sketch the force diagram. For car, there's the constant resistance of 4,500 Newton pointing left. The thrust in the rod points right. Using Newton's second law, T minus 4,500 equals 1,500 A. For trailer, there's only thrust, pointing left. So, minus T is 500 A. Add the two equations. Minus 4,500 is 1,500 A. So A is minus 3 meters per second square. Therefore, the deceleration is 3 meters per second square. And T is 1,500 Newton. Remember to set the positive direction of the acceleration. Forces in this direction are positive, and forces against this direction are negative.